Welcome to the workshop. Today we want to take a look at the depth first search algorithm. And while you can find the explicit algorithm in many places, we won't discuss the details that you might see in a description of the algorithm in its formal written out form. Here we'll just talk about the depth first search algorithm as just the idea of the process by which it is, or the process that it is. All right, so in this example there are four things we want to do. We want to apply the depth first search to this graph. We want to then use that depth first search to find a spanning tree for this graph, and then we will want to list all of the back edges that are given from the spanning tree that we find, and then we also want to label our edges in the original graph with directions, so that way we can obtain a directed graph, but we want to do it in such a way that the graph is strongly connected. Excellent. So the first thing, again, we want to do is apply the depth first search algorithm. And in this, all that we're interested in doing is numbering each vertex and giving a predecessor for each vertex. And it doesn't matter which vertex we start with whenever it's not specified. I would like to start with A as an arbitrary choice. So in this case, what we can actually do is we can label this vertex with a number 1. In the breadth first search algorithm, we were identifying distances from a particular vertex to every other vertex. So we started with 0. In this case, we can start with 1 because we're not looking at distances. All right, so label A with 1, but in this case, it does not have a predecessor. Now, in the depth first search algorithm, all that we're interested in doing beyond this is just arbitrarily choosing a vertex which is adjacent to A, or whichever one we just labeled. And we continue this until we can't reach any further in terms of going to a vertex which is not already labeled. So we're building up our set of labeled vertices. So we have A labeled, but that's it so far. So we're going to follow along this edge here to B. This one will be labeled 2 with predecessor A. And all that I'm doing here is I'm just moving along, arbitrarily choosing an edge to follow. So let's see here. Next, I'm going to travel along this edge down to G. So I'm going to label G with 3, and it has predecessor B. All right, now I'm going to travel, let's say, up to D, and I'll label this with 4, having predecessor G. Again, I'm just choosing arbitrarily an edge to travel along to another vertex. The goal here is to travel to a vertex which has not already been labeled. Once I hit a vertex that does not have any edges to unlabeled vertices, then I have to go back. So we'll see that in just a moment. So I traveled from A to B, then B to G, then G to D, and now I'm going to travel from D to C and call label C as 5 with predecessor D. But now that I'm at C, if I travel down, I would be going to G, which is already labeled. And if I travel along this edge to B, I'd be traveling along an edge to a vertex that's already labeled. So once I get here, I have to backtrack to the previous vertex. I have to backtrack to the predecessor. All right. Now at D, do I have any other choices? Could I have gone anywhere else? Well, no, I don't. I don't have any other choices. There's nowhere else to go. So I don't have any more vertices that I could label following D. So I have to backtrack again. So I backtrack to G. So here here at G, I do have some options, right? I can go to H, or I could go to K, or I could go to J. So what I'm going to do, just to make things a little bit interesting, is I'm going to travel along J. Now, I'm just increasing the labeling by 1 each time, so J is labeled with 6, and predecessor G. Then I'm going to travel along along this edge to K, and K will be labeled with 7, with having predecessor J. And then I'm going to travel up along this edge to H. This will be labeled 8, with predecessor K, because I traveled from K to H. But now at H, I no longer have anywhere else that I can go that is not already labeled. So I have to backtrack. I have to travel back to the predecessor, K. Do I have anywhere else I could have gone at K? No. Okay. Well, so we backtrack to J. Do I have anywhere else that I could have gone at J? Well, yes. Yes, I could have actually taken J over to I, or I could have taken J over to F. So let's do that. All right. So we travel, let's say, it doesn't matter which way I go here. I'm going to end up completing our labelings here. So let's go up and say this one is, right, I've already used 7 and 8, so I'm at 9, having predecessor J. And then I'm going to travel down to I, so this has label 10 with predecessor F. And then I'm going to travel up this edge to E, so E has labeling 11, and it has predecessor I. Excellent. So we have successfully applied the depth-first search algorithm to this graph. Again, we obtain a labeling for each vertex by beginning with 1, assigning label 1, moving to an adjacent vertex and assigning label 2, moving to an adjacent vertex, assigning label 3, and continuing on until we can't move forward anymore. In this case, we looped around and got ourselves stuck here. So we had to backtrack to G, where we then, let's see here, went to J, then to K, then to H, and again, we got ourselves stuck, nowhere else to go, so we have to backtrack to J, and J we had options again, so we went up to F, down to I, up to E, and there's nothing else to label. Now, as far as the algorithm itself goes, and a nice formality, what you would find is that you would end up backtracking E to I, to F, to J, to G, to B, to A, and once you get back to the beginning, you would say, as long as there's no options, then you would be done. So that's one way that you can terminate the algorithm. Otherwise, the algorithm is terminated once all of the vertices have been labeled. All right. So again, we have successfully identified a labeling for each of the vertices. Now what I'd like to do is I would like to redraw this graph, or redraw all of the vertices, and then just give the tree that we have obtained from this. So I've got 1, 2, 3, 4 vertices, 1, 2, 3, 4 vertices, 1, 2, 3. All right, so I've redrawn all of the vertices. I'm not going to label them A, B, C, D. I think that it should be pretty clear with what the labels are. But I began at A, and then I went to B. Now, what you could do is you could simply take, you don't have to follow along any special pattern. You just have to attach each vertex to its predecessor, and that's it. So A is attached. You don't have to attach it to anything specifically because it has no predecessor. B gets attached to A because A is the predecessor. Excellent. C gets attached to D because it's the predecessor. D gets attached to G because it's the predecessor. E gets attached to I because it's the predecessor. F gets attached to J because it's the predecessor. This isn't looking much like a tree yet, but by the time we're done, we should find that it is. Alright, so we attached F to J because J was the predecessor. G gets attached to B because that is the predecessor. H gets attached to K because it's the predecessor. I gets attached to F because it's the predecessor. J gets attached to G because it's the predecessor. And K gets attached to J. So now you can see that we have a graph which does not contain any cycles, and all of the vertices are connected to one another, which means it is in fact a tree. And this is a subtree, this is a spanning tree of this graph. Excellent. So that was the second objective. We gave the labelings for the depth first search, and then we provided the spanning tree for the graph. The next thing that we want to do is we want to identify the back edges. Back edges. Now there are quite a few back edges here because there are a lot of edges in this graph. So what I'm going to do is I'm going to try to list them all in a methodical way. So I'm just going to list the ones along this edge that are not used, and then the vertical slash oblique ones here, and then the horizontal ones, vertical slash oblique, and then these horizontal ones here, whichever ones are not given. So remembering that an edge can be described as a two-element subset of vertices, that is, we can just give the two vertices that the edge is between. So this edge is not part of the tree, so we have BC is one edge, that is BC. CD is used. This vertical edge, AE, is not. Let's see, this vertical edge, BF, is not. This oblique or slanted edge is used, so that is not a back edge, it is a tree edge. This edge here is not used, so it is a back edge, that is CG. This vertical edge is CG, we just said that one. This slanted one is used here. This horizontal one is not used, so EF. Nothing there. This horizontal one is not used, so GH. Again, I'm identifying the edges that are not in the tree. These edges here are called tree edges. The edges that are part of the graph but not part of the tree are called back edges. So I'm just listing the edges which are in the graph but not in the tree. Excellent. So this vertical edge is used, this slanted edge is used, this vertical edge is used, this slanted edge is used, this vertical edge is not. So GK. GK is this edge. GK here is that vertical edge. This slanted edge is used. This horizontal edge is not used. IJ. And this horizontal edge is used in the tree. So this is the collection of back edges for the graph. Now, they get their name back edges, I believe, from how we find a strongly connected graph within this graph. Or we obtain a directed graph by labeling directions to each edge, and we can obtain a strongly connected graph using a particular method here. For all of the tree edges, for all of the edges here, what we want to do, of course, we're just going to label this graph, but for all of these edges, what we want to do is we want to label them with the direction going from the smaller number to the larger. So here, this edge which is contained in the tree, we want to go from the smaller number to the larger number. So we get that direction. Let's see here. This edge is not used, that edge is, but the direction is this way. Let's see here. This edge, 2 to 3, so we can connect using that direction. And then this edge, 3 to 4, we would use this direction. Let's see here. This horizontal is not used, that one's not used. This one, 10 to 11, would go that direction. This one here, 9 to 10, would go that direction. This edge here, 6 to 9, would go that direction. Let's see here, 3 to 6 would go this direction. See, vertical is used, slanted. This guy is used, so 6 to 7 would give us that direction, and 7 to 8 would give us this direction. So that's all of the edges that are part of the tree. Now we'll go through and label the edges that are not part of the tree, which is simply everything that needs to be given a direction yet. So this edge, instead of traveling from lower to higher, what we're going to do is we're going to travel from higher to lower. So for all the back edges, instead of traveling forward along the tree, we're traveling back along these back edges. So 5 to 2, because it's a back edge. 11 to 1, because it's a back edge. 9 to 2, because it's a back edge. 3 to 5, 5 to 3, because it's a back edge. 8 to 3, because it's a back edge. 11 to 9, because it's a back edge. 10 to 6, because it's a back edge. And that is all of our edges that have been labeled. Excellent. So we have given a direction to each of these edges, creating a directed graph, and what results is a strongly connected graph. So you should find that there is a path between any two vertices. Of course, a path which travels in the indicated direction along each edge. Excellent. I hope you found this to be helpful and enlightening for the depth-first search algorithm. Of course, take this idea that we discussed and then review the actual algorithm in a more formal version and compare. Observe what we did here within a formal written out algorithm. Hopefully that will help you understand how to read algorithms in general, if that's something that you're working on. Excellent. Thank you again for joining me today. I will see you again back in the workshop soon.